talked about the foundations of quantum mechanics, where it came from, the background historically, etc., as well as the experimental basis for it, why it was even proposed in the first place. And I made an analogy to the present state biology, which also has a few examples only to back up the claim of some quantum phenomena at work. I'll come to it a bit later, but before I do that, I want to go through some nitty-gritty of what quantum mechanics is, so we need to understand the ramifications for biology. It doesn't have to be literally the same implementation as it is in physical objects, particles, but it can be somewhat metaphorical. So the first postulate of quantum mechanics is that of what is a quantum state? What is a given quantum object described by? And that's the postulate about the state function. Functions, without again going into mathematical details, it's a complex function of position and time, which is kind of abstract. You can think about it metaphorically as a cloud. It's a distribution of probabilities. The square of it is actually the probability density, probability per unit of volume, of finding this given object, particle, molecule, somewhere in space at a given point in time. That's the first departure from deterministic classical physics, where everything has its place in position and time. Here it is spread out. And actually over time it spreads out even more. Now it's called the evolution of the state function. And the second important point here to be made is a complete departure from classical thinking about objects, because it allows the object to be at the same time in different states. It's called the linear superposition principle. So, a particle like an electron or proton or neutron or even a given atom can reside at the same time, in fact, in principle, in an infinity of states, allowed by the system's conditions. We captured what it means. And the introduction of this wave function is credited to Erwin Schrödinger, Nobel Prize in 1933. And this is the only way you can actually predict the evolution, the future of any physical systems at the quantum level by seeing how the wave function changes over time, and that means how probabilities of finding it in a given state evolve. So these are some formal properties of the wave function. I don't want to belabor the point. The thing is that it has to be such that when you integrate or add up all the probabilities, it has to be one. So there's no source or sink of particles, namely you have the freedom to occupy different states, but at the end of the day, the sum of all the probabilities must be one. So it's the conservation of the mass conservation, if you wish. So these are continuous functions, as I mentioned earlier, kind of like a cloud, which changes shape, by the way, as it evolves, flattens out, diffuses. And this is the only way through which we can predict or calculate physical properties of the system described by the wave function, because as you'll see in next postulate and the one after, properties are built into the edifice of quantum mechanics through the wave function. The probability distributions I mentioned of being in a given state is equal to the square of the absolute value of the wave function, and then the measurement of a particular physical property, be it velocity, angular momentum, energy, or things of this nature, linear momentum, are performed mathematically by the action of operators differential operators on the wave function. And this is called the eigenequation, which means that the operator, let's say in this case it's momentum, which is the spatial derivative, the second entry into this table. Operator momentum, in classical physics, momentum is mass times velocity. Suddenly here, it's this weird thing with h, Planck constant, divided by I, square root of -1, and multiplied by partial derivative with respect to position, dx, that's how you pronounce this funny symbol. So this is in classical sense, that will be mass times x component of velocity. So x component of linear momentum is simply obtained by acting with this operator on the wave function and returning the wave function with a multiplier factor. And that factor is actually the value, predicted value of the momentum of the system with this particular state given by the wave function. So it's highly counterintuitive. I think you have to be kind of somewhat crazy to come up with this way of describing something as simple as momentum. But it makes eminent sense if you, in the context even of historical development in classical mechanics, Lagrangian mechanics, Hamiltonian mechanics, all of these properties parallel what we know about classical physics, but at a higher level of abstraction with operators replacing simple multiplication. Energy, likewise, which, as you may recall from even high school, energy is the sum of potential and kinetic energies, right? And potential energy depends on in which potential the particle resides. Kinetic is 1/2 mass velocity squared, or momentum squared divided by 2m, as you can see here in this last entry. So that gives you an idea how energy is constructed in quantum mechanics. You square the momentum operator, which I just introduced, divided by 2m, and add the potential function v of x. And then this is a differential operator, actual second order differential operator in terms of the spatial derivative. You act on the wave function, and that returns the wave function pre-multiplied by some value, and that value is the energy of the particle in this given state. So once again, very briefly, state is what a particle can be found at, and the state could be, for example, moving with being there and moving with a particular velocity, having a spin, which we haven't defined yet, but I'll do it in a minute, pointing up. That's a state, but the particle may be in several states at the same time. And until you do the measurement, you don't know which state it is. But in principle, it can be an infinity of states. Each state has an associated number of values of these physical properties, and each physical property can be obtained by acting with an analogous operator on the wave function. Easier said than done. You have to do it, 1,000 times to practice it and to be good at calculating these things. The Hamiltonian is the operator which defines the energy of a system, and this leads us to the fourth postulate of quantum mechanics, which was formulated in 1926 by Schrödinger, which basically is equivalent to Newton's equation of motion. I don't think you would recognize it as such, but it is really, in a nutshell, a formula for finding all physical properties of a given state, especially solving for eigenenergies. That means energies of the system allowed by the conditions in which the system is in existence. And that also leads to something which is a very, so the Schrödinger equation, canonical fundamental equation describing our microscopic reality of the world, spelled out here at the top. You can also find time evolution of the system by acting on the wave function with this time the derivative dt multiplied by IH, and this leads to the equation that gives you the evolutionary change of the wave function over time. So these are the postulates. They seem, I'm sure, quite abstract, but all of that has been tested over a century and works incredibly well, with, of course, as always, some limitations, because what I've shown you is actually non-relativistic quantum mechanics, which applies to particles moving at relatively slow velocities, not approaching the speed of light. When you use accelerators and particles become very, very fast, then there is a different version of it. You have to improve a little bit on this. It's called the relativistic quantum mechanics, and the Schrödinger equation is replaced by something called the Dirac equation. Paul Adrian Dirac was a British physicist who also got a Nobel Prize, incredibly brilliant, and basically improved on the non-relativistic version provided by Schrödinger. Okay, so this is kind of a take-home message in a few sentences about something which is generally accepted in terms of interpreting, because this things I showed you are really mathematical, heavy mathematical abstractions, which need to be interpreted to be in the form of digestible physical meaning. And this physical interpretation is called the Copenhagen interpretation. Copenhagen because Niels Bohr, another Nobel Prize winner of that time, was at the University of Copenhagen, and he was instrumental in providing concrete interpretations. So it says, for a quantum system, because it's actually in a superposition of states, there is no reality until you perform the measurement. So it's in this cloud of possibilities, not only a cloud of the wave function, but superposition of wave functions, which gives you, an infinite number of possibilities. But when you measure it, then the system has to declare one of these states as that in which it is manifested in this experiment. Now, this is the good news. The bad news is that after the measurement is completed, the system will evolve and escape basically a predictability again. So repeated experiments will give you the snapshots of evolution, but in between you don't know the fate of the system. So everything is, in terms of probabilities, I told you that the square of the wave function is the probability density. They have to add up to 1. And when you do the measurement, it's called the collapse of the wave function. Instead of having these numerous possibilities, now you have to collapse it on 1. What is this? It's like asking somebody a question, yes or no. There's no maybe or in between. However, okay, so this is the Schrödinger equation. I'll skip that. We talked about it. It can get actually quite hairy when you start. So far we've talked more or less about a system which is singular, let's say single particle, electron, proton. Then things complicate when you have many particles, and you can have a quantum system composed of, in fact, infinitely many particles and still be in a quantum regime. Then you have to add up all the energies, create a Hamiltonian, which is the sum of all the individual Hamiltonians, and also interactions between the particles or interacting part. And the wave function, now what is the wave function? The wave function of the combined system actually is the product of the wave functions. So things get really complicated, but that did not deter chemists, because chemists were the first ones to take the torch to the next level from physicists, and they used it to describe molecules, in fact composed of many number of atoms, many electrons, many protons, and then you have to create these complicated wave functions called molecular orbitals. Okay, so this is the guy that I mentioned called Dirac, that systematized not only systematized quantum mechanics, but introduced relativistic version of quantum mechanics, and a beautiful representation, very simple, using instead of the functions, wave function psi and phi and so on, chi, Greek letters galore, he used symbols, bra and ket, and the probability of transition from one state to the other is the overlap between wave functions for the two states, and it's called bracket. So there's a lot of kind of wordplay. The bracket is the probability that a system changes from one state to the other, but Dirac separated this into the bra, one state, and the ket, the other. Very clever. And this is how you symbolically go into complex structures. We need that because if you want to go to biology, then this complexity here is laughable, it's so simple. But we need to take gradual, small step, baby steps. And the first baby step here is, for example, to represent the Hamiltonian, or the energy of an atom, and then a molecule, where you add up all the potential energies and the kinetic energies and the interaction energies. So here you see for the first time a term. So these are potential energies of individual electrons, and this is the interaction between electrons, Coulomb interaction. So now the game becomes quite complex, but this has been solved, and that's the Schrödinger equation for a system of electrons, let's say in an atom or molecule with interaction between electrons, and then you find what is this good for? Well, if you solve this equation, and if it's a complicated thing, you need to use computers to solve it, write complicated equations and solve them, differential equations, solve them with boundary conditions, and obtain energy levels. Why is this important? Because if you obtain energy levels of atoms, then you can find transition between energy levels, and these are spectra, energy spectra for, let's say, helium or hydrogen or bromium or chlorine, fluorine, whatever. Once you know the spectra, you can analyze the light coming from stars, distant stars, and say, I see helium there on a distant star in this galaxy, and then there's water molecule on Mars or somewhere. So you don't have to go there, you just look at the spectra, and the spectra correspond to the energies separating those levels that you've obtained by solving this equation. So I think it's an incredibly powerful intellectual game that becomes practical because you can understand the universe even at light years of distance from you, as well as you can do spectra of air molecules in the atmosphere, and you can then measure things like the concentration of carbon dioxide, and the greenhouse effects, and pollution, etc., etc. Everything starts here by properly setting up the problem and finding out the blueprint, maybe a fingerprint, I should say, molecular spectroscopic fingerprint of each atom and each molecule. Each of them has a different spectral characteristic, a different set of energy levels. Okay? So everything boils down to transition between energies. This was another major figure in that time, Wolfgang Pauli, a Swiss physicist who got the Nobel Prize in 1945, and he came up with something even more bizarre, namely, and hugely important, because without this we couldn't have understood the table of the elements by Mendeleev, namely spin. Spin is a property of so-called fermions, and Pauli defined it. It's an additional property of quantum systems, and I'll tell you why it's important even for biology. And all quantum particles can be defined into two groups: fermions with half integer spin, which means 1 half, 3 halves, 5 halves, etc. And bosons with integer spins. And fermions can only exist as a single particle in a given state. They don't allow two particles in the same state. Therefore, that gives you exclusion principles for occupying energy states in atoms, for example, because you have orbits with energies, and then electrons can have different angular momenta and then spins up, down. There's no third possibility for them. They have 1 half, so it's plus 1 half, minus 1 half. And that's how you build up the, fill up all the orbits, and you gradually go from the lowest energy level to the highest, filling these energy states and occupying spin states with up and down possibilities. Without spin, there is no magnetism, and magnetism is a common phenomenon known to us and known to ancient Indians and Greeks and Egyptians. Magnets, you can have a frigid magnet, and very few people understand and know that it's a quantum phenomenon because there's no magnetism without spin. Orientation of spin particles, alignment in one direction gives you the powerful magnetic interaction of your fridge magnet. If they are randomly oriented, there is no magnetic interaction. They have to be aligned to give you a strong force. So it's a macroscopic, room temperature, or even higher phenomenon based solely in quantum mechanics. There is a so-called Van Leeuwen theorem that demonstrates the classical interactions do not and cannot lead to magnetism. And bosons are those particles which have integer spins, spin 0, spin 1, and they allow actually to have an arbitrary number of particles in the same state as opposed to fermions, and that leads to all kinds of, we call them collective excitations. So now we have, if you go into systems of many particles, remember we started with a single electron, single proton, then we have the atom and start putting electrons in orbits. Now you can think about solids, crystals, with many atoms and molecules. All of this is quantum mechanical down at the bottom, and you have interactions between them that can lead to interesting phenomena. For example, spin waves, these spins that I talked about, up, down, well, they can now, through space, propagate, and that leads to quantum excitations called magnons, spin waves. So now we have macroscopic properties of systems, solid systems, magnets, crystals, etc. I want to say cables, but this is plastic, maybe it's not so quantum. At the bottom it is, everything is, but not so easy to explain. But it's easy to explain regular crystal lattices and their vibrations. Their vibrations are also quantized. Not every vibration is allowed, and quantization means energy packets. So these are examples listed, just names, of collective excitations in solids, all of which are quantum quasi-particles. Quasi because a particle in our mind is a localized object, but quasi-particle is something like a wave, a collective excitation. So many atoms or molecules react coherently. They propagate excitations through space, and you can then measure properties of such collective excitations, including phonons, lattice vibrations, which leads us very close now to biology. But before I make a link to biology very briefly, showing you that, and importantly, because now we go into, so we start from individual particles, several particles, atoms, molecules. Now we have collections, many, let's say 10 to the 23rd, Avogadro's number, macroscopic number of particles, and now we occupy them in states. We still have, we have to still respect the rules of quantum mechanics. Fermions can occupy each state singly, that is one fermion per state. 1 or 0. This doesn't show you 0, but you can imagine. And you can think, or some of you may already think, that's neat. Maybe we could use it for quantum computation. And that actually is one of the frontier areas of quantum computing, spintronics, using spin as quantum, or qubits, quantum bits, right? Spin or photons. Photons would be quanta of light, electromagnetic wave can also be used for quantum computing. But photons are bosons, so you can have as many as you want in a given state. For fermions, you have only 0 or 1, okay? So that's spin half, fermions, bosons, arbitrary number, and you can distribute them. And this is classical. In classical physics, we have something called Maxwell-Gibbs-Boltzmann distribution. Particles are arranged according to energies in an exponential function. The higher the energy, the lower the probability, or the fewer the particles. And this is also driven by temperature, and temperature allows particles to go to higher energy levels because it provides thermal energy. And so you can see now the differences between the classical distribution, quantum distributions, fermion, Dirac type of distribution. Very different, right? And if you were now do the calculations for this, there are some mathematical details which I'll spare you, but the slides have them, so I'll provide the slides. If you're interested, there's a slight difference in the, this is a probability distribution of having energy epsilon for bosons, and for fermions the difference is only in the minus versus plus sign. The rest is the same. And of course, if you go to the classical case, there will be a 0. So classical is plus 0, fermions plus 1, bosons plus minus 1. So subtle but important. For fermions, you have a step function describing the probability of being in a given energy state, and that changes with temperature. By the way, this little diagram has major implications for electronics, because electrons are fermions and they obey this kind of probability distribution, and semiconductors, semiconductor technology utilizes it in terms of providing the basis for transistors and diodes and things like that. So, and this is a graphical comparison between these three cases. Remember, plus 1, minus 1, and 0. Classical in the middle, Maxwell-Boltzmann. The bottom is Fermi-Dirac, and top Bose-Einstein bosons. Probability distribution, or in other words, the number of particles for a given energy. Now, why is this important? Because if you want, and the efforts are going on, if we want to demonstrate the presence of quantum excitations in biological systems, for example, all living systems emit electromagnetic waves, photons. If we want to show that there is a quantum nature of those systems, we need to demonstrate that the probability distribution of the energy emission absorption, either way, is not that in the middle. It's not classical, it's quantum, so it could be Fermi-Dirac or Bose-Einstein. So that would be an indirect way of demonstrating quantum nature of living systems. There has been quite a bit of literature on biophotons, and the verdict is still out, the jury is out. But we do know, so to close the argument about, oh yeah, quantum mechanics is only for microscopic particles, in the first half hour of this lecture I tried to convince you that it's not just tiny particles, but their collections as well. In fact, infinite collections of quantum particles give rise to quantum effects, such as the phonon statistics or spin waves, magnons. But the second aspect is that thermal noise, finite temperature, we all live at room temperature, physiological temperature. We experience a very small variation of temperatures, all of which are quite high. By physical standards, that means these temperatures would cause so-called decoherence of quantum systems. They would not be easily characterized by a single well-defined wave function, but constant interactions would destroy it. So to counter it, I assembled these 5 examples of finite temperature quantum effect, macroscopic quantum effect, although superconductivity is still far away from the room temperature. It's minus, I think that minus 100 Celsius, the highest temperature at which superconductivity has been demonstrated, superfluidity even lower. But then you have laser action, phonons, semiconductors, and magnets, all of which are finite temperature quantum systems, macroscopic quantum systems. Okay, so then beyond that, and I will stop talking about the foundations of quantum mechanics. I think we've said enough. And this is the only slide that kind of gives you a vista into the modern versions or representations of quantum physics. Quantum mechanics was supplanted by quantum field theory, which explains basically all of the structure of the subatomic particles, including their interactions, quarks, Higgs boson, and basically provides unification of all the forces of nature except for gravity. Quantum dynamics, quarks and gluons, including antimatter, which again Dirac predicted the existence of antimatter. In other words, electrons with a positive charge, protons with negative, and incredibly powerful energetically collisions between them, or annihilation processes of matter with antimatter. We seem to be living in a universe composed of matter only, luckily, because if it was a mixture, explosions like nobody's business. Maybe there's another universe with antimatter, complete mirror image of what we see here, who knows? Everything seems to be symmetric, more or less, why not? So, this is where we are at today. We have the so-called standard model that puts everything in an elegant formalism, mathematical formalism, complete, explaining everything again, except for gravity. It's a very annoying, quirky business of combining classical gravity. Of course, gravity is a weak, very weak interaction and operates on cosmic distances. The other things are microscopic, tiny. Not necessarily just microscopic, mesoscopic as well, maybe even beyond. And that's what we'll try to explore here. Now, this is a list of gifts of quantum mechanics. Why is it so useful to at least discuss quantum biology? First of all, without quantum mechanics, there would be no stable atoms, because we have electrons orbiting, as we talked today about the nucleus, in stable orbits. They are not falling down and canceling the charge, plus of the nucleus minus of the electrons. So only quantum mechanics can explain the stability of atoms, and by extension stability of molecules, by extension stability of everything that is based on molecules. So that's the first gift. Then of course the fact that this is, it points in space and trajectories in time become quite complex in terms of wave functions, with molecular orbitals, atomic orbitals being quite symmetric, but yet non-trivial, and changing shape on interactions, providing covalent bonds, sharing electrons. All of it is is wonderful and providing us with a great playground for creating complex systems. And then entanglement, quantum correlations between particles that I briefly mentioned allows for some mysterious interactions which seemingly seem to be unphysical. Coherence, another phenomenon that is characteristic of quantum, like in lasers. That means collective oscillation with a single frequency, at least from the point of view of coordinating activities, is an attractive proposal for implementation in living systems. Quantum information, incredible amount of information storage and processing allowed by the introduction of qubits instead of bits, instead of just 0, 1. You now have the circle, and many more amounts of information can be stored. Then stochasticity, in other words, introduction of probability instead of deterministic Newton's equations that Simon de Laplace so confidently proclaimed to be determining the future of the universe. The universe is not clockwork. It's not like that. Although before this lecture we talked about living in a matrix. So there's, if we live in a matrix, somebody has set up the rules, and somebody has set up the rules, and we without knowing the rules, follow them somehow. I guess it's possible, but it would have to be, the rules would have to be more or less probabilistic. And there is in the theory of probability the law of large numbers. That is, if you have a large number of objects, then over time they evolve to the statistical average. So averages make sense for large numbers, for small not necessarily. But if we talk about a universe of or 8 billion people, that's a large number, and we individually may think that we have free will and follow our own rules, but collectively the universe may be evolving to some state that is predetermined, at least probabilistic. I don't know if you agree with this kind of interpretation of the matrix, but
yeah, I think there are many different variations of it that could be true. Yeah. Okay,
so that's my interpretation. I still want to believe that I have free will, and all of us do, but collectively maybe we behave as coherently coupled particles, and unfortunately sometimes that results in terrible events. I don't want to comment on the politics and events of the day, but you know what I'm talking about, that sometimes people en masse behave differently than individuals, and sometimes turn into something else. Okay, so we talked about quantum statistics, which again adds to the complexity, and tunneling, allowing for events which normally classical mechanics would not allow, improbable or impossible even, catalytic reactions with energies insufficient to transfer an electron, but in the case of quantum particles, the probabilities kick in, and what is impossible in the classical case becomes probable in the quantum case. Maybe not highly probable, but if you have sufficient number of repetitions, you will eventually make it. Okay, so one of those theories that inspired some mathematical biologists is the quantum theory of solids. So now we are going a little bit into the microscopic area where quantum phenomena manifest themselves, and that's, phonons, crystal lattice vibrations in a coherent sense, not as sort of random waves on the lake, but organized oscillations propagating through the crystal, and that can be quantized. And this is actually one area of application where Albert Einstein made a mistake, or at least his theory was proven wrong, because he assumed the crystal to be composed of independently vibrating molecules, And that led to a very different result than what experiments demonstrated. You can measure the specific heat of a solid as a function of temperature, and at low temperature, specific heat of a solid. Specific heat means how much heat you have to provide to the system to increase the temperature by 1 degree. Right? So that's the specific heat of a solid. You can divide by mass, and that gives you a number. And you see how much that change in temperature. So for solids, such as crystals, at low temperatures, this specific heat C depends on the third power of absolute temperature in kelvins. For high temperatures, it becomes constant. Einstein got the right answer for the high temperature, but the wrong answer for the low temperature. He got an exponential function instead of cubic. And he failed because he assumed something which is wrong, that atoms do not oscillate or vibrate independently, they actually oscillate collectively, and these collective oscillations or waves, called phonons, are quantum particles. So then you use that in the quantum statistics, Bose-Einstein statistics, where I showed you, and from that, like turning the handle and doing many pages of calculations, several at least, you obtain the right result. This is the wrong result by Einstein. This is the right result obtained by Peter Debye, a Dutch physicist, also a Nobel Prize winner. And so that was seemingly minor, but actually monumental, because it showed that microscopic fingerprints of quantum effects can be seen on large objects. In this case, something easy to measure, like specific heat. This has been, around for a century and a half since the first industrial revolution. People are measuring specific heats of liquids, solids, and gases, and everything. So that was well known. And now suddenly, after a century and a half of analysis, you come up with something and say, my goodness, that tells us that these oscillations, these phonons, are quantum quasi-particles, and the solid is not just a regular object, but it's an object with internal dynamics that is ruled by quantum principles. So why am I saying this? Because we'll see in the next lecture, when I finally get into the nitty-gritty of biology, that something very similar applies to energy transduction in living systems. If you assume, so let me just emphasize it because it's an important point. For crystals, Einstein incorrectly assumed independent oscillations of little atomic centers. Debye showed that they are creating collective waves, which are quantized. So quantization occurs by how many wavelengths you can fit into the space, basically. So it's a wave function, okay? It's just like shredding a wave function, but for a large object. Now, I'll show you next time that the same approach can be used to explain so-called allometric scaling laws of physiology, which basically measure the amount of energy, metabolic energy, transduced by an organism depending on its size. And an explanation for this can be found by assuming that mitochondria, or some equivalent energy-producing organelles, are not independent. They are coupled. So in other words, enzymatic reactions involving energy transduction in living systems are collectively operating in a wave-like fashion. So if you introduce quantization principle like the one that was introduced by Debye for solids, now apply it to enzymes in living systems, animals, even plants, you obtain a hallmark of quantum behavior. So that's the argument for quantum metabolism. And metabolism is one of the essential features of living systems. Without metabolism, there's no life. For plants, of course, we have photosynthesis, so it's not the same as, but photosynthesis is quantum in nature par excellence. This has been demonstrated independently. Now metabolism is on an organism-wide scale, coherent or synchronized. And I think that also leads to the efficiencies, et cetera, et cetera. We'll come back to this topic because I think it's fundamental to life. This is just the list of several important advances which were made possible by quantum physics. All the consumer electronics, computers, laser scanners, MRI, NMR, X-ray, crystallography, solar batteries, photosensors, photodetectors, all of this, PET scans, even GPS, would fail if not for the quantum principles at play. I mean, there's of course engineering, optimization, etc. All right, let's move gradually into the theme of this lecture series, namely biology, and we have to understand where we are coming from. And I think it's a truism to say that all of matter must follow the principles of physics, but it's not obvious that physics is the name of the game, so to speak, for biology. There are some special rules for biological systems, one of which is the Darwinian evolution, which you cannot derive from physics. So there are rules which are independent of physics. They are not violating physics, but physics is not instructing us specifically about evolution, adaptation, natural selection, these kinds of things. Right? Okay, so having said that, we see here how so far we actually, I don't know, the arrows should be, this is top down, showing you, I want to go from the bottom to the top, from quarks to elementary particles, to nuclei, to atoms, to molecules, to large molecules consisting of on the order of 1,000 atoms. So far, everything up to this point, the bottom layer here, can be well described by either quantum physics or quantum chemistry, with some difficulty going into large molecules, macromolecules, where things, simply we don't have computational power to predictably characterize these systems. And then beyond that, we're talking about here, we're talking about proteins, DNA, macromolecules of cell biology. And this is where the boundary between quantum and classical becomes completely fuzzy. There are some proteins which have been analyzed and shown quantum degrees of freedom, so there is that. But globally, I would say protein biochemistry is not based on quantum physics in any way, to my knowledge. There may be some reaction centers which are characterized by quantum wave functions, but not the entire protein necessarily. And then we go into systems of proteins, complexes, microtubules, filaments, actin filaments, membranes, all of that, which is at the mesoscale. And we don't know if this is the realm of quantum or classical biology. There may be some hallmarks of quantum behavior, and this is where, in my opinion, the focus should be. There is actually, and maybe I'll come back to this, reasonably robust literature on the function of ion channels as quantum tunneling devices. There is argument to be made that ions, as they go through the channel, tunnel quantum mechanically due to their speed, efficiency, and so on. There is evidence for some proteins absorbing quantum mechanically electromagnetic energy, transducing it. But as a whole, the cell is not really routinely understood to be a quantum system. We're talking about 10 to the 10th atoms, 10 billion or more, even the simplest like E. coli, bacterium, and more complex even more. This is where things break down. It doesn't mean that there is no room for quantum physics. It's just that we are not smart enough to use it, or we don't have the computational infrastructure large enough to run these things. There was a project here at the University of Alberta, I would say about 10 years ago or 15 years ago, called the Cybercell, Project Cybercell by Mike Ellison.
Yeah.
Remember that?
Yeah.
Well funded. I think he got millions of dollars, many millions. And so I'm just telling you what the limitations exist in terms of simulations. And he simulated an E. coli cell by representing, I don't know if it was every molecule, but a large percentage of molecules as classical balls. Basically, they can stick, they can unstick, they can be transported and diffuse. And he obtained some interesting results, spontaneous division, cell division under some conditions. But that was the computer limitation at the time. He had a supercomputer, I remember, got a lot of firepower, computational power, spent millions on that, and that eventually got recycled, I guess. But the point is that that was the limit. I mean, let alone representing every atom quantum mechanically. That was simply 3 plus 1 dimensional simulations of balls colliding and moving around. Admittedly, more than a decade ago, so today these computers are maybe 100 times more powerful, maybe 1,000 times. We could do more. Whether we can represent the entire molecular machinery of the cell quantum mechanically, I would say no. So it doesn't invalidate the point that the cell, it's in its synchronization of activities, a living cell, is very likely, in my opinion, to utilize quantum degrees of freedom and operate, especially in terms of coherent behavior, in terms of perceiving the world outside, signal transduction, and response to signal. And now we go to the organism level, even the smallest organism, single cell organisms. Now we're talking about large numbers of atoms and exploding numbers of possible combinations of behaviors. So that's kind of a segue to dimensions, and that gives you the scale of masses. What we talk about with quantum mechanics in terms of masses is, let's say, atomic units, which is the unit daltons, or hydrogen mass is the unit. We have water 18, everybody knows. Amino acids 110. Nucleotide unit, so nucleic acids, between 309 to 324. Each unit, I think it's still graspable by quantum means, but then when you create a string of DNA with 1 billion base pairs, you throw up your hands and say, I'm sorry, this is beyond my capabilities. Cells, prokaryotic cells, 5 to 50, 10 to the 10, so 50 to 500 billion hydrogen masses. Eukaryotic cells, the dimensions, micrometer scale. Now we're talking about trillions, hundreds and thousands of trillions of hydrogen masses. So that's the real barrier for computation. It's just very difficult. We can focus on aspects of it, but not en masse. We can't do that. So Cybercell, I mentioned the E. coli. There are some other projects out there. University of Washington had another one. So people are trying, even classically, to represent the entire cell mathematically and implement simple physical rules to find out if we can simulate the behavior of individual cells. This is the scale of dimensions, spatial dimensions. For me, the lower limit is 10 to the minus 10, 1 angstrom. That's the size of half an angstrom is hydrogen atom, right? That's the smallest unit for us in biology that makes sense. There's no point in going to quarks and looking inside the atom. Then you have nano world from 1 nanometer, several nanometers at the size of a protein, 5 to 10 maybe, across, up to 100 nanometers is what's called nanobiology, nanotechnology. These are the dimensions. And in this fuzzy world where quantum and classical effects meet is most of what's interesting in cell biology, because that covers pretty much all the individual structures, right? The membrane has a thickness of about 4 to 5 nanometers. The protein is about 5 nanometers. Microtubules have 25 nanometers across. They are micrometers in length. So that's outside of it a bit. Until recently, we used the word microworld, microscopy, and micrometer. Now we're talking about nanometer, going deeper. Right? So, and then sizes of cells, E. coli as small as 2 micrometers, red blood cells up to 5, and then larger cells, tens of micrometers, neurons even meters, hair, and so on, humans, meters. So this covers about 11 orders of magnitude in terms of sizes. And at the bottom you have also the corresponding wavelengths of electromagnetic waves that can be used for observational purposes, right? So you have X-rays being the shortest wavelength, allowing us to see individual atoms, other than hydrogens, but every atom other than that can be seen. That's why you use them for crystallography. You can find the structure of the protein. Then you have ultraviolet, and that means hundreds of nanometers, so it's not visible, shorter than, so 300 maybe. And visible then, very narrow spectrum, 400 to 750 nanometers visible light. What our eyes perceive as the world, our external world, can you imagine how narrow this slice is? That's what we see. Doesn't mean that everything else is not there. It is. We just don't see it. We see only a tiny, tiny spectrum of electromagnetic waves, which we are immersed in, right? From X-rays, cosmic rays passing through us all the time, to all the way to microwaves, terahertz. Infrared is thermal excitations, so this is infrared, longer, about 900 nanometers and up to thousands of nanometers. Microwave, micrometer is 1,000 nanometers, and so on. So visible is used for observational microscopy, confocal microscopies, right? But you can also obtain other spectra. So that's what we see, and if we don't see, it doesn't mean it doesn't exist. Most of it we don't see. So our imagination is limited by our ability to see things, unfortunately. Okay, and this is another comparison. Now this is time scales of biological processes, starting from sort of below here. This is this is a microsecond. Microsecond is already a pretty long time by biological standards in terms of vibrations and of chemical bonds. Vibrational changes occur on a picosecond, or fraction of a picosecond, 10 to the minus 12 scale. Sadly, our computer simulations of atomic structure of proteins, for example, end here, about 100 nanoseconds, 10 to the minus 8, 10 to the minus 7 right here. So this is where we operate, from picoseconds to hundreds of nanoseconds in terms of computer simulations, which take into account all atom simulations. That's why I told you, and that's classical, by the way, doesn't have any quantum diffusion. And all of this is the realm of biology, including the life on Earth, that has been here for about 4 billion years, which is 10 to the 17 seconds. So if we start looking at it from the chemical bond oscillation picosecond timescale, 10 to the minus 12, and go to the age of the scale of the time and life on Earth, that's 29, almost 30 degrees of freedom, and 30 orders of magnitude, I'm sorry, on the biological timescale is unimaginable. Imaginable. And likewise, our perception of the world, okay, that's important because how we understand what's happening around us. Visible light, 400, 750 nanometers wavelength, that's what we see. Our perception of events, it's actually snapshots, is about 100 milliseconds. So 1/10 of a second is the granularity of our perception of time. If something happens faster than 0.1 seconds, we don't see it. We simply don't. 10 to the minus 1. This is, and then that's how long we live. That's our life. And finally, the energy scale. Okay, this is just for reference. I don't want to spend too much time other than to say that because life takes place at physiological temperature, that corresponds to the 0.6 kilocalories per mole, which is free for every degree of freedom. Every moving particle or molecule gets this much energy for nothing because it's simply at this temperature in the human body. So all energies below that value are meaningless. This is the value of energy from which you can start assessing what's important, what's not. And the second number I want to point out to is quantum of biological energy, GTP or ATP, mainly ATP. Hydrolysis provides about 60 kilocalories per mole, which is about 100 times greater than KT. And that's why all the biological molecular processes in biology are deliberate, not left to chance, like DNA transcription, translation, protein synthesis, motor protein movements, active transport. All of these processes use at least one molecule of ATP per step, just to make sure. You see, this is 100 times, this is very smart, it's 100 times greater than KT, therefore nothing is left to chance in this case. Nothing is left to probability. It's deliberate. These are other bonds at play when you construct biomolecules, yes.
So when you said nothing is left to probability, does that mean it's not quantum anymore?
Well, not necessarily. It is quantum actually in a way that the quantum energy in the form of ATP is so large that it provides a given process a direction. It is not subject to, I want to say, maybe I misrepresented this. Thermal fluctuations would provide decoherence. If it's a quantum process, it can be directed, but it can be coherent, just like I mentioned coherence in lasers, right? So you want that. Thermal energy is random, and it's classical. So thermal energy would provide decoherence and destroy directionality. In this case, directionality means, let's say, the process of creating a protein from the genetic code, based on the genetic code. That has to be faithful. There occur errors, mutations, as you probably know, maybe one in, I don't remember now, 100,000 or 10,000 events is wrong, is incorrect, and that's how you accumulate mutations. But it's a very small fraction, and could be explained on the basis of this ratio that KT is only 1% of quantum ATP energy. It means overwhelmingly the odds are against a random event, but these are just probabilities. Maybe 1% or less, 0.1% will be just like, I don't know if you're familiar with motor proteins, like kinesin and actin, they move on filaments, and you see sometimes they make the wrong step, sideways or back, or they fall off the filament. So these things are allowed, probabilistic, but their odds are very, very small. So that's what I meant. I'm not saying that this excludes quantum. It simply says that there is a coexistence of, let's say, quantum energy, biological energy in the form of ATP, GDP, deliberately utilized for one direction of the process, but noise, however small, is there, and sometimes you can see the effect of noise on making an error. And I would say it's not a judgment statement, because I think mutations are biologically, by and large, useful, right? If we didn't have mutation, there would be no evolution. The living forms would be stagnant. They would not be able to evolve, adapt, and improve. So this built-in minor percentage of mutations is beneficial overall. Although some mutations are detrimental, you may have mutations leading to diseases. Some 1/3 of Alzheimer's, I think, is genetic, and so on. But for the life forms in general, it plays a good role. Okay, I think we still have a few minutes left. I want to, yes, so this is where kind of the difficulties of combining fields emerge, because I showed in this diagram how different fields of intellectual pursuit have not only their own elements, but also their rules of the game and interaction between the elements. So elementary particle physics, as we've seen, involves quarks and nucleons and their quantum interactions. But from the point of view of solid-state physics, fundamental physics, all of that is insignificant except for the electron, proton, neutron. Everything inside of these particles never manifests itself. We don't need this. So electrons and protons give rise to solids, and their interactions, Coulomb interactions by and large, are sufficient to understand how this is built. By the same token, chemistry involves ions, really, that make molecules, atomic interactions, and covalent and other bonds are the only thing that you need to worry about. And from chemistry to biochemistry, what do you need? Nucleic acids, amino acids, phospholipids, sugars, maybe some alcohols. And these are the elements and their rules of engagement, so to speak, how they interact, how they form polymeric forms, strings of nucleic acids in the form of RNA, DNA. You don't need, in fact, this at all. You don't need this. You need a little bit of that. Everything else is shortcuts from the biochemistry developed over the years. So that's why it's so difficult to jump from here to cell biology, which is the next level of abstraction, where actually bits of biochemistry are needed, and then you form larger structures and involve empirical rules rather than foundational physical rules. So everything respects physics, of course, but that doesn't mean that you have to use Schrödinger's equation to understand biochemistry or cell biology yet. Okay. Once we find a sufficient number of examples that are quirky enough to call for that, then, and this is how modeling is done, by the way, in terms of, remember I talked about length scales and time scales, and these are different types of modeling, theoretical models employed in the various ranges. So quantum mechanical models, typically, if you buy off-the-shelf software, quantum mechanical, quantum chemical software, you would be using it for hundreds of picoseconds and maybe a few nanometers. This is where this is at play. Then you go into molecular dynamics, molecular mechanics, atomistic models. Every atom is represented as a ball, classical ball with bonds. So we're talking about hundreds of nanoseconds of simulation time and micrometer dimensions. This is where that is at play. Beyond that, you so-called coarse-grained models, where you don't have every single atom represented, only groups of atoms lumped into as a single ball. Let's say each amino acid is a point with a mass, or nucleic acid. And that's how we would represent a cell, such as an E. coli cell or other types of cell. And then if you go into milliseconds, longer time scale, and millimeters, now we're talking about cell tissues, organs, and so on. You develop continuum models with fluid dynamics, thermodynamics, and some solid state physics in it. That makes sense, and not only makes sense, but actually introduces real combinatorial barriers. This is a famous number, immense number. It's not. It's a technical term. It's not everyday term. 10 to the power 110 is a number which tells you what is the real barrier for computation. And this is, the number is obtained as the product of the atomic weight of the universe in protons, assuming that the entire universe is a computer. Every single atom is a computing unit. Computing things, so the idea of this matrix, but kind of variation on the concept of matrix. Performing computations since the Big Bang, all its existence. So the age of the universe is about 14.5 billion years in picoseconds, because picoseconds, remember, are transitions between states and atomic states. So if every atom in the universe was a bit, flipping states every picosecond for the age of the universe, then you'd have the largest supercomputer imaginable. The entire universe is one computer. That product gives you the computational capacity of the universe being a computer, and that's 10 to the power 110. So if you can find a set of objects which is that big, you can say that it's impossible to inspect that set, let alone do any operation on it entirely. And you might ask, well, yeah, but that's an astronomical number. Where do you find sets which are that big? Actually, it's very common. I'll give you, I don't know if I have a slide with examples, but I'll give you just a couple of examples. There's no marker here, is there? All right. For example, well, the first example is the number of DNA sequences. So each base pair, there are 4 possible nucleic acids, so it's 4 possibilities, and the length of DNA is, let's say, 1 billion base pairs. So 4 to the power billion is vastly larger than that. If you wanted to, let's say, find out which mutations in the DNA will do what, and inspect all possible mutations, it's impossible. It's just a simple, not possible. Don't even start, okay? So there's one example. Another example is the number of possible amino acid sequences making a protein. So you have 20 possible amino acids, right, in nature. And a protein may have 500, on average, 500 amino acids in a string. So it's 20 to the power 500 is the number of possible proteins of length 500. It can be 400, 300, 600, you get the picture. So biology is full of examples of immense number sets, in principle, right? And therefore, if you say, well, maybe in a few years I'll see a copy of myself, a twin or a look-alike, that person will have to have an identical DNA to yours, right? I mean, the set of possible DNAs are so enormous that the odds of this happening are really, really zero. All right? So that kind of gives you the perspective on complexity and diversity in biology. There are barriers that cannot be overcome, and there is no computer that we can construct on this planet that will tell us, you know, which proteins are, which mutations, which proteins, out of all the possibilities will do this or that. We can guess, we can come up with educated guesses or some fragmentary simulations, but not exhaustive. The same with, let's say, arrangements of neurons in the brain. You know, we have 97 billion neurons to be specific, and they may be interacting with each on average 10,000, but could be anywhere from, let's say, 100 to 100,000. And how many combinations and permutations of brains you can construct with the same number of neurons blows your mind, pun intended. All right, so we've reached this point at the end of this lecture, which started Erwin Schrödinger, whose name was mentioned a few times today. What is life? And he was actually asking, in this context, several questions, one of which was whether living systems have some sort of quantum coherence in them, which still is an attractive proposition, coherence, because, you know, your little finger knows what your toe is doing or your eye is doing. All of this is connected and synchronized, and integrations of information is amazing. How can this be done? Cannot be done in a step-by-step domino-like process. It has to be collectively, almost instantaneously. All of these things are possible within quantum mechanics, not possible classically, at least my knowledge. So that was the first. He actually even proposed that memory is stored in aperiodic crystal lattices, and by the way, proteins are called aperiodic crystals. He didn't know it at the time. So possibly protein conformations could be where information is stored in the brain. But the most important question he asked is, how is it that life, against the second law of thermodynamics, lowers the entropy? And that actually today can be explained. Living systems are created as a result of structure formation, entropy reduction, organization, order. Physical systems do the opposite. Left to themselves, they create disorder, chaos, and increase entropy. So this book, I don't know, this is a misprint. I think the book was published in 1943 or 44, if I remember correctly, during the Second World War. It is an amazing read, 80 years ago, today, more or less published, still valid as a foundation from which physics of biological systems can be developed. Okay, so Kim, I think I'm done for the day.
Okay.
Cool. So in the next lecture we will finally delve into the topic of quantum mechanics and life. I think I built the foundation, telling you what quantum mechanics is known to apply for sure, how it is applied, what's involved, and what physical scales are involved in biological systems. And now we'll see whether we can actually explain something biological using quantum physics. Thanks.
Yeah, it's exactly 80 minutes, so
Okay.
that's cool.